So we are very happy to have Sayak Chowdhury from Boston University. He's going to talk about online reinforcement learning in large and structured environments. He's currently a postdoctoral associate in the Division of Systems Engineering at VU. He was a Google PhD fellow at the Indian Institute of Science before coming here. His research interest lies in sequential decision making, specifically multi-armed bandits and reinforcement learning. Is also interested in multi-agent learning problems and learning under privacy and fairness constraints. And take it away, Sayak.
Okay, thank you for arranging this talk, and thank you, Venkatesh, for this introduction. So in this talk, I will talk about online reinforcement learning in large and structured problems. Some part of the work was done when I was a PhD student at Indian Institute of Science, and a very brief part of the work is it's been done when I'm postdoc here at VU. Reinforcement learning is concerned with learning to take actions to maximize rewards by trial and error in environments that can revolve in response to actions taken by an agent who is operating in that environment. The typical goal of a reinforcement learning agent is a search goal. That is to find a policy with high total reward using as few interactions with the environment as possible. A different but related goal is the optimization goal. Here, the goal of the agent is to maximize total reward or equivalently minimize its regret due to not knowing the optimal, not knowing the environment advance. So there are a couple of example applications where this optimization goal is significant. For example, recommendation systems where a user's click leads to a revenue. So an agent will always try to maximize its revenue. Like sequential investment, where how much you invest in different portfolios guarantees your total income. Similarly, dynamic resource allocation is also an example. In this setting, there's no separate budget to purely exploring the unknown environment. So the agent needs to act in a way so that the exploration and exploitation must be balanced carefully. So in this talk, I will talk about reinforcement learning algorithms for regret minimization in large and structured environments. Specifically, in the first part of the talk, I'll focus on a degenerate reinforcement learning model called the multi-armed bandits model. In the second part of the talk, I'll focus on Markov decision process. The main challenge that we'll be addressing in this talk is how to generalize learned knowledge across unseen states and actions in the environment. So part one is about online learning in large-scale multi-armed bandits. Let me first give some background on the multi-armed bandit problem. And there are n arms with unknown reward parameters mu1 to mu1. You can think about the rewards are coming from a Bernoulli distribution. So how a multi-armed bandit algorithm typically operates? At time 1, say the agent decides to pull the arm number 2, and after pulling the arm, it gets to observe a reward y1, which is generated from the Bernoulli distribution with mean mu2. Say at time 2, the agent pulls the arm number 1 and correspondingly gets a reward y2, which is generated from the Bernoulli distribution with mean mu1. Similarly, say time 3, the agent pulls the arm y3 and gets to see Bernoulli reward with mean mu3. The learning progresses in like that. Say time 4, it again picks the arm 2 and gets to observe the reward from that Bernoulli distribution. And given a time budget capital T, say at the last round, the agent picks the arm number capital N and gets to see the reward coming from that distribution. So what is a possible strategy for the agent to select these arms so that its rewards are maximized? Note that the agent doesn't know the mean of this parameter, that is mu1 to mu1. So a well-known benchmark and a well-known algorithm is the upper confidence bound algorithm introduced by Auer. The idea here is to be optimistic under the uncertainty. Specifically, at each round, given whatever the observation he has received, the agent builds maximum likelihood estimates or simple sample means from the observations. Say sample means for all the Bernoulli distributions 1 to n is denoted as mu1 hat to mu1 hat, mu1 hat 1 to mu1 hat n. Since the environment was not known a priori and an arm is not pulled sufficiently enough, then its estimate is not good. Say arm number 1 was not pulled sufficiently enough, so mu1 hat is probably not a good estimate at this point of time. So to account for this uncertainty about this estimate on the arm which has not been pulled sufficiently often, what the agent does, it actually correct this sample mean with a variance correction term, which is inversely proportional to the number of times the arm has been played, which you denote here by ki. And then it add it up with the sample min and simply play the arm which maximizes this upper confidence bound envelope. In this figure, you can see that all the upper confidence on the rightmost point of the confidence envelopes are been denoted by this red dot. So basically, whichever arm gives you a higher value of this red dot, that arm will be played. This rule inherently trades off between the exploration and exploitation problem. See, if we have a good estimate of the sample mean of the mean through the mean of the unknown parameter, then the rule will encourage you to play that arm. However, if an arm was not been pulled sufficiently enough, that means ki is low, the rule will encourage to pull that arm so as to get more and more observation from that arm. It has been shown that this simple strategy works extremely well in practice, and also theoretical guarantees have been proved. There are other variations of the Bandit problem also. So in the standard multi-arm problem, the Bandit problem that I have described, the arms rewards are independent of each other. So mu1 to mu1 are independent, are a mean of independent Bernoulli distributions. However, often in practice, more structure or coupling can be present between the different arms rewards. For example, consider different arms sitting in this two-dimensional plane. Here, each arm I is a vector xi of dimension 2, and playing an arm it gives a reward which is a linear function of the arm's features. And the coefficient of this linear functions denoted by theta is unknown, and the rewards you observe is just a noisy version of this linear function. Here, as you can see, all the arms rewards are correlated with that parameter theta. So how can one build an algorithm in this case? So one well-known algorithm is the lean UCB algorithm, which actually first build a point estimate. Typically, it's a least square estimate or the maximum likelihood estimate, theta t hat, and to take care of the uncertainty around the lack of knowledge of theta, it builds a confidence region, or which typically takes the form of an ellipsoid around this maximum likelihood estimate theta t hat. So after it builds this ellipsoid, the agent plays the most optimistic action with respect to this ellipsoid. That means it chooses the action which gives you the highest possible reward for any point from this ellipsoid. So it also turns out that this algorithm works well in practice, as well as give a good regret performance. So in this talk, which is the main focus of this talk will be, is to generalize linear bandits to arbitrary functions. So this problem is also called black box optimization. The problem setting is as follows. we need to maximize an unknown utility function f, which is defined on a domain D. We can only sequentially query f with points x1 to xt drawn from this domain D. After drawing every point, we get to see noisy evaluations of these functions yt, which is f of xt plus epsilon t, but we assume epsilon t to be a Gaussian noise, or you can also extend this to sub-Gaussian noise setting. Our goal is to maximize the expected utility over a budget of capital T rounds, or equivalently minimize the cumulative regret due to not knowing the optimal point of this function that is denoted by x star. This black box optimization problem has several applications. Consider the application of hyperparameter tuning in deep neural network. There are a lot of hyperparameters involved when you train a deep neural network. Some such as the learning rate of the deep neural network, the regularizer that you use, number of hidden layers or number of units that you put in each layer. Even if the optimizer that you use like AdaGrad or Adam, you can also think about as a possible hyperparameter. And also similarly, the nonlinearity function like ReLU or softmax that is used can also be thought of as a possible hyperparameter of the deep neural network. So we can cast this deep neural network training as a black box optimization problem. In the notation of the previous slide, here D is all possible hyperparameter configurations of the neural network. Fx is the training error for a particular hyperparameter configuration x, and x star simply denotes the best set of hyperparameter, that is the set which gives you the lowest possible training error. The main challenge is there are huge or possibly infinite set of hyperparameters to choose from. That means learning rate can vary from in a continuous set, or the number of hidden layers you can vary from 1 to say from 100 or thousands. So how can we proceed, or how can we build a good learning algorithm in this setup? So there are a couple of heuristic approaches like grid search or random search. They just divide the domain in grids and just pick points from each grid, or just pick some points randomly from the grid. The main issue that they face is that they do not use information from previous searches, and so they're not good when point evaluations are very expensive. Like in a deep neural network training the neural network once can take a couple of hours or so. So you cannot just keep on training for exhaustively train for all possible points in the space. So we need to make an education decision about where to search next. And the idea that gives us to do this is the Bayesian optimization. Here we put a probabilistic model over the unknown function f. Then we use model predictions and uncertainties about this model to select the next query point xt. Finally, after we query the model xt and observe the data yt, we update the posterior belief about this model with this data, and then we keep on just repeating this. To make this more formal, let us now put some regularity assumption on what kind of black box function f which we'll be considering in this talk. Specifically, we consider f to be an element of an reproducing kernel Hilbert space, which is associated with a kernel function k defined on the domain D. By that, what we mean is you take a point x in the domain D and map it to the space of to this reproducing kernel Hilbert space with a feature map phi x. Then the point evaluation of the unknown function f at this point x is simply an inner product of f with the feature function phi x. Similarly, say if you have another point x prime and you map it to its feature function phi x prime, and you take the inner product between phi x and phi x prime, then you get back the kernel function k, which is defined on the domain. So you can see that there is a good interplay between the feature function and the kernel function and the unknown and the point evaluation of the function f. So we try to use this good inner product property of the reproducing kernel Hilbert spaces to build our algorithm. Another important property that we need is the smoothness of the functions. And by definition, if the function has small norm in the reproducing kernel Hilbert space, then by Lipschitz property, it induces a smoothness on the functions. That is, if 2 points x and x prime are small enough in the RKH space, then their evaluations at the function is the difference in the evaluations of function values are also small enough. So now we present our algorithm design philosophy. The idea is to use Gaussian process regression, which is very popular in machine learning. So recall that the utility function f is unknown. So we model the uncertainty of this about this in utility function f using a Gaussian process prior, which is characterized using a min function, which here it is 0, and a kernel function k, which is the same kernel function of the previous slide. Then after say we gather a couple of data xt and yt, and the posterior about f after getting these t noisy observations are also seen to follow a Gaussian process distribution, with the posterior mean is given by the function mu tx, and the posterior kernel is given by the function kt x, x prime. This simple Bayesian update rule allows us to design our algorithm as follows. So recall that at every round t, we have a posterior model over the Gaussian process. So the idea is to use our old friend UCB to design an algorithm in this setting. That is, to choose the point which have highest upper confidence bound. Specifically, at each round t, we choose the query point xt, which maximizes the combination of posterior mean and the posterior standard deviation of the Gaussian process. Here, bt is a regularization parameter which is tuned to guarantee that the performance of the algorithm is reasonable. Note that this algorithm is not new. It has first appeared in a hugely popular work by Srinivas and co-authors as GP-UCB. What we improve upon, we provide a tighter regret bound compared to them. Specifically, we prove a order of log t improvement in theory. That's why we call this algorithm as an improved version of GP-UCB. Specifically, our regret bound takes the form of order of gamma t square root of t with high probability. The one important quantity to note here is gamma t. It signifies the information complexity of the problem in hand. It captures the reduction in uncertainty after observing the noisy rewards. And as is evident, it will also depend on the kernel function or the RKHs that you are operating on. Let us dig deep on how this quantity behaves. Now consider a function f randomly drawn from a Gaussian process with min 0 and kernel k. Then evaluated this function over t points x1 to xt, and stack them as a vector. Then you pass this vector from an IID Gaussian channel with a noise variance sigma square, and observe the output, which is just the function values plus the noise. Then gamma t, or which we call as the maximum information gain about the unknown function f, is defined as the maximum mutual information between the output and the input of this channel. As we see, the function f is depend on the kernel function k, and so the gamma t in turn also depends on the kernel function k. It has been shown that gamma t behaves logarithmically for some popular kernel functions like the RBF kernel or like the Madan kernel, or at least sublinearly. So now if we plug this value of gamma t in our regret bound, which will behave sublinearly, we can we see that our regret bound also behaves sublinearly with respect to total number of rounds t. At this point, let us now discuss another possible algorithm that one can design in this setting. This algorithm is called as Gaussian process Thompson sampling, and it is inspired by a Bayesian philosophy. So what is a natural strategy for a Bayesian to do? So given a posterior distribution or a distribution in hand, a Bayesian simply samples a random function from this distribution and just choose its maximizer at its query point. The idea of Thompson sampling goes back to Thompson, which was first developed in 1933. Specifically, introducing it to our problem as follows. So at each round, recall that we have a posterior over the unknown function f. So it's just sample a random function ft from the GP posterior. And then we just play the query point xt, which maximizes this random function. It turns out that this algorithm also performs pretty well theoretically. That is, it achieves the regret bound order of gamma t square root of t. However, there is a small square root d factor blow up in the regret compared to the UCB algorithm, which is mainly because of the extra randomness injected due to this Bayesian principle. Okay, so we also compare our algorithms to some of the other baselines that have been proposed before. The left side figure. In the left side figure, we sample a function f from RKHS, and we compare our algorithm GP-UCB and GP-Thompson sampling with some baseline which are called probability of improvement and expected improvement. And we see that our algorithm IGP-UCB improves over GP-UCB and also over all other algorithms, and also our GP-Thompson sampling algorithm also fare well. We apply this to a to detect the maximum temperature in a room from some sensor measurements, which was collected in Intel Berkeley Research Lab. And here also we found that our algorithms performs similar, if not better, than the other baselines. So we also considered a variation of the above problem that we talked about. Recall that we in the previous problem we assumed that the noise to be Gaussian or at max sub-Gaussian. How about the noise does not have good tail property like Gaussians? Say the noise exhibit heavy-tailed behavior. The motivation behind considering this problem is as follows. The distribution of delays in communication networks typically known to exhibit heavy-tailed phenomena. Similarly, bursty traffic flow distributions or price fluctuations in financial data exhibit heavy-tailed properties. So in this work, we assume that the noise is heavy-tailed. That means not all the moments of the noise are bounded. Specifically, if we assume that only the second moment of the rewards or the noise is bounded, then we can develop variant of the Gaussian process UCB algorithm and Gaussian process Thompson sampling algorithm that we have described before, which results a sublinear regret. The takeaway from this work is bounded second moment is sufficient to get order of square root t regret. We do not need a bounded moment generating function assumption like sub-Gaussian noise. So this concludes the first part of the talk, which is on bandits. Now I move to the second part of the talk, which is on online learning in large-scale Markov decision processes. So specifically, we consider learning in an episodic Markov decision processes described by a state space S and action space A, both of which can be subset of Euclidean spaces. An MDP is always characterized with a transition probability distribution, which is a map from the joint state action space to a simplex over the state space. There is also a reward function, which is a mapping from the state action space to a interval between 0 to 1 that we consider for simplicity. We work here with an episodic setting, and we fix the episode length to be capital H. Typically, at each episode, the learning works as follows. The environment starts with a state S1. The agent chooses an action A1 and get to see a reward R1, which is a function of the state S1 and the action A1. Then the environment moves to a new state S2, depending on the current state S1 and the current action A1. In S2, agent selects another action A2, observes the reward R2, and the environment moves to the new state S3. This goes until the terminal state is reached, which we denote by SH plus 1. That means the episode length H has been exhausted. In this work, we will consider parameterized MDPs, where we assume that the transitions are parameterized by a vector theta, which is unknown to the agent a priori. For example, consider this simple queuing system. There are n states, and it is a discrete time Markov decision process. And the queue are characterized by a Bernoulli lambda arrivals at every state. And now at every state, there are only two possible actions, mu1 and mu2. So if we take the mu1 action, that means you move from state, move to the next state. If you take the second action corresponding to this Bernoulli mu2, then you move back with the previous state. So we assume here that this mu1 and mu2 are known. That means there are uncertainty only in lambda. So transition probabilities are characterized by this lambda, and it is unknown. So to get hint, after getting hint from this example, we now formally describe what reinforcement learning, what a goal of a reinforcement learning agent is in this online setting. Note that the MDP parameter theta is unknown to the decision maker a priori, and the agent must also always learn the optimal policy. That means what action to take in each state to maximize its cumulative reward gathered over this entire episode. Or equivalently, we can pose this as a regret minimization problem, due to which the agent suffers due to not knowing the optimal policy, here denoted by A star in advance. The agent always faces this trade-off: explore the state space and use current knowledge to design good policy. So it turns out that the same UCB or upper confidence bound based approaches can also be designed in this MDP framework to build good algorithms. The idea here is to build confidence intervals per state action pair and be optimistic with respect to these confidence intervals that you build upon this entire state and action spaces. Couple of well-known algorithms include Rmax algorithm or the popular UCRL2 algorithm. The key idea that were presented in these works are to maintain estimates and high confidence sets for transition probabilities for each and every state action pair. Both the algorithms work perfectly good when a number of states and number of actions in MDPs is finite. However, if number of states and number of actions are in the MDPs are very large, or the transitions have structures and relations between them, then building confidence set part state action pair is wasteful. To this end, we considered the problem of parameterized MDPs. We assume that the transitions are described by a finite dimensional parameter which is unknown to the agent a priori. A classic example of a parameterized MDP is the linear quadratic regulator. Here the state transitions are governed by two matrices A and B, which are unknown, and the reward transition and the reward functions are governed by two matrices P and Q, which are typically known. So the unknown parameter theta for this particular example of MDP is the joint matrix A, B. There are other examples of parametric MDPs that has been recently considered in the literature, which includes the bilinear MDP by Yang and Wang, and also the linear MDP by Jin. In both the works, they have assumed the feature function phi, and nu are known functions. In Yang and Wang, they consider the bilinear MDP model, where unknown parameter is M, which is a matrix, and in Jin et al, they have considered a linear MDP model where the unknown parameter is a vector. These models are perfectly good to capture the tabular finite state finite action MDP. However, they suffer some drawback. For example, they do not cover the several popular models like the one that I have mentioned before, the linearly controlled systems. This has not been captured by any of this work. Also, there is a model called factor MDPs where there are parent-child relation between different states and actions. That model is also not covered by this work. So motivated by this, in this work we consider the linear exponential family model. Specifically, instead of assuming the transition probabilities are linear, we assume the log of the transition probabilities are linear. Formally, the exponential family model is defined by a unknown parameter theta, which is a vector, some known feature function f, which is also the sufficient statistics of the family, and a log partition function or the simply normalization function z. The good point here is that the exponential family can capture a wide range of distribution that you can even think of, like Gaussian, Bernoulli, Gamma, chi-square, or even heavy tail distributions like Pareto and all. Those are also captured by this exponential family model, which gives us a lot of flexibility to work. So here we build a algorithm which is inspired from the upper confidence reinforcement learning algorithm in the exponential family model. The key idea here is to maintain estimates and high confidence sets for the unknown parameter theta. Specifically, at each episode t, we compute the maximum likelihood estimate theta t hat from whatever data, that is the state, actions, and the next states we have seen so far. So after building the MLE estimate, we build a confidence set around this MLE taking on the specific geometry, I would say specific information geometry of the problem into account. For example, in the confidence CT, we include all such possible parameters theta, which are close to the MLE estimate theta t hat in the KL divergence distance. I'll talk about how this confidence sets looks like in some good example families a bit later. So finally, after computing the constructing this confidence ellipse at CT, the agent compute the optimal policy with respect to the entire set CT. So he can probably use value iteration or simulation techniques to do this computation. In this work, we do not care about the computational issue and focus on the theoretical guarantees. So after computing the optimal policy, the agent play the action which is prescribed by that policy. So we now show that how this algorithm performs theoretically. First, we prove a generic concentration inequality on the exponential family model. Specifically, we show that the unknown parameter of the exponential family theta lies in the confidence set CT that we just built using this scale divergence geometry with high probability. This result is indeed actually a general result to design high confidence set for adaptive regression in conditional exponential families, and it has application beyond this particular problem. For example, this result generalized known results for linear bandits and also GLM bandits. Now we apply this concentration bound to the particular reinforcement learning problem at hand, and we show that our algorithm Exp-UCRL attains a sublinear regret with high probability. Specifically, the regret bound is of the form d square root of t, where d is the dimension of the parameter. There are some unavoidable constants sitting in the front of the regret bound also, that is alpha and beta, which are model dependent constants and encode the degree of non-linearity that has been introduced due to our shift from the linear model to the non-linear exponential family model. However, note that even with this constants, which can typically be shown to be bounded for typical examples like linearly controlled systems or L keyword, we get that order of square root t regret scaling. Not only that, we can capture a lot of different probability distributions. To this end, I just take a small digression and highlight the importance of the general result that I just talked about before. That is the design high confidence sets for adaptive regression in exponential families. It turns out that this result can be presented as a general toolkit to build confidence sets in exponential families, and it has applications well beyond bandits and RL. For example, we can handle both the discrete distribution and both Gaussian both continuous distribution with this result. Like we can build confidence set for chi-square random variables, which has not been explored in the statistics community. And we can show that with high probability our confidence envelope, that is the yellow line is the upper confidence and the blue line is the lower confidence, that all that converges to the true unknown true parameter of the distribution after sample size of say 100 or something. Similarly, we can build confidence sets for Gaussian distribution when both mean and variance of the distribution is unknown. Here the mean and variance are the true mean and variance is given by the red star, which is 1,1, and we can show how the confidence set shrinks as we increase the data points. So the yellow ball is like for data point of 100 or something.
Sayak, one question I had, sorry to interrupt you. How do you measure these confidence sets? In the Euclidean case, it was clear. In the general cases, what
general cases it has been measured is like this. So you take all the parameters theta such that the KL divergence between the transition between the probability distribution, which is parameterized by that parameter theta, and the your estimate maximum, like it can be a maximum likelihood estimate, and even we have a result for map estimates also. You can take also a map estimate and take the transition distribution, take the probability distribution with that estimate.
So I ask this question simply because there are many ways of defining what the right geometry has to be, right?
Yeah,
One
exactly.
could have described a more general measure on probability distributions. You picked one. I guess the proof is in the pudding. If this is useful in ultimately proving a regret bound, great. But in general, how does one think about coming up with the right way to measure distances?
So in
Here you use
exponential
KL.
family, it turns out the Bregman divergence, or simply the KL divergence reversed, is a good geometric measure because of the log. Because you can see because of the log partition function that is available to us. If you know the log partition function, the form of the log partition function, you can compute the Bregman divergence, and you can use that as your distance measure. And as we have seen in this work, that that our confidence sets, say I have shown this for chi-square or Gaussians, and we have a confidence set for Bernoulli, exponential, Pareto, and you name any. We have confidence for everything, and we have compared them to a couple of other baselines that just do typical sample mean concentration. And
do you have a precise result for reinforcement learning using these exponential?
Yeah, exactly. The precise result is what I just described before.
Oh, this is the regret
this
bound.
This is the precise result in exponential family reinforcement learning problems.
And D is what? H is what here?
D is the dimension of the parameter theta, and H is just a function of the MDP dynamics.
I see.
So the takeaway is that we have a general tool.
There are results such as square root of SAT and so on, right? In
exactly.
learning, how does that compare with your bound?
Okay, so this square root SAT results are for tabular MDPs. So what we show in this work, we consider the MDPs where S and A can be potentially infinite. So instead of writing the bounds in terms of potentially infinite S and A, we write the bound in terms of the parameter dimension D. However, our this concentration bound can be applied to the tabular MDPs also, and we get the similar scaling. So basically, in tabular MDPs, we will apply the Bernoulli concentration, and I think it will be possible to get the similar scaling because as we see experimentally, our confidence sets behave similarly as the confidence set that has been built in the literature using sample mean concentration. Okay, so the takeaway here is that using this exponential family model, we can possibly handle a lot of distribution other than Bernoulli or Gaussian, which are probably, or exponentials, which are probably the only ones studied in the literature. However, we can generalize beyond that, like two families Gaussians and chi-square, Pareto, Poisson, Weibull, anything. So that I just wanted to mention the general applicability of this result. So in couple of minutes, which I have left, like in 10 minutes, I will talk about application of RL result to the important problem of differential privacy. So reinforcement learning is widely applied to personalized services, like providing personalized healthcare to patients, giving some virtual assistants, and social robots for tutoring kids, or in the recommendation systems. However, note that both states and rewards contain user sensitive information. Like in the healthcare example, user's age, her gender, or the treatment history might be considered very personal or sensitive information. He or she might not want to share that with any other people. Also, like in virtual assistants, the words, the voice, and the sentences that we speak or type could carry a lot of personal information of ourselves. Like you're sending some personal messages to someone. Similarly, in social robots, the facial expressions of the kids and the scores they get on puzzles might sometimes be considered as very sensitive information. Also, in online recommendation, the shopping habits of a particular customer or his or her preferences or age or gender can be considered as sensitive information. So how can we protect all this information in a theoretically rigorous way? A good approach to tackle this is the notion called differential privacy. There are two models of differential privacy. One is the central model, where the users trust the learning agent with all its personal data. And it's up to the learning agent to decide how to protect the user's data so that an adversary cannot infer any user's data by observing the output of the agent. That means how to come up with a learning rule which protects the user's private information, as well as ensuring good performance. Another privacy model that has been studied is the local model, where the user do not trust anyone with his data, and he or she protect his or her data at the local site. So the learning agent only can observe private data from the users and then build on top of this its favorite learning algorithm. So the question we wanted to tackle is, can we have a unified framework for both models in the reinforcement learning problem that we are discussing? So in this talk, we'll just only focus on the tabular MDPs. However, the results generalize beyond tabular MDPs also. So what are the private information in tabular MDPs? Number of visits to a state action pair, SA, denoted by NSA, is a private information. Note that it can be captured using only bits 0 or 1. That means whether a state action pair has been visited or not. Similarly, number of transitions to a given state S prime from the state action pair SA. It is also can be captured using bits. And also the rewards are also rewards RSA are also private information, which are scalars, but eventually if we rewards are bounded, it can also be we can also work on using the similar principles that we will work on the bits. The goal of the algorithm is to release private counts of these numbers NSA, NS prime SA, and RSA with a minimal amount of noise injected. Now the protection in the local model, where each user is responsible his own protection. It typically goes like that: each user K add independent noise to her data, which leads to sum of total capital K noise, and K is the number of rounds that a learning algorithm will go on. However, the protection in central model can be done efficiently by using a binary tree counting mechanism, where only log K noise needs to be added. But note that a local model gives you a stronger notion of privacy because your data is protected at your own end. However, the central model might not give you that stronger level of protection because the agent might be some agent might not be trusted at all sometimes. So we show that we can build a policy optimization algorithm which can handle this privacy requirement under the both central and local model. Similarly, we can build a value iteration algorithm under the additional notion of differential privacy for the both central and local model. I do not go into the specific details of the regret bound in the interest of time, but I do point out that the regret will increase if the level of privacy increases. That means if epsilon is a parameter governing the privacy, where low epsilon means your privacy protection is low, then low epsilon means your privacy protection is high. Then by the regret expression we can see that if epsilon is very low, then the regret is high. That means to ensure better privacy, we need to suffer more in the regret bound. We have compared our private policy optimization algorithm in the left and private value iteration algorithm in the right with the non-private policy optimization, where there is no requirement of privacy protection, and non-private value iteration, there's no requirement of privacy protection. And we see that the non-private bound is this blue line which is at the bottom, and the regret in the central model, that is green line, is pretty close to the non-private bound. That means the central model of notion of privacy can be achieved without suffering very much on the regret. However, the regret in the local model is higher compared to the central model. This is intuitive, since the amount of noise added in the local model is higher. This happens because in local model you get better protection. So this privacy and regret trade-off you can see from these plots. Another important part is to know that if epsilon is lower, then your regret is higher. That means higher level of privacy protection also needs higher level of make you suffer higher regret. To this end, now I will conclude this talk with some current or future work that I'm planning. One work I'm pretty much interested is model selection in bandits and reinforcement learning. If you recall, we have till now we have assumed that the function class or the class of transition distributions in bandits and MDPs are known. That means we have assumed the class of the exponential family distribution, that class is known. Or in bandit, we assume that the RKHS function class, that the kernel function is known. But in practice, typically these classes are also not known. So how to identify this correct model class during the learning process? So I would like to characterize this theoretically in both bandits and MDPs. Similar to the privacy question that I've talked about, I'm also interested to think about the fairness and transparency in policy selections or action selections in reinforcement learning. I'm also equally interested to study the peer-to-peer learning or federated learning frameworks in multi-agent systems, and study the property of networks and communications, etc. To this bandit and RL problems. Okay, so I conclude my talk here, and yeah, let me know if you have any questions.
Just a quick question. Very interesting talk, by the way. But I'm wondering if there are lower bounds for that somehow relate to the upper bound you've shown for reinforcement learning with exponential families.
No, we are not able to show any lower bound for exponential families. In fact, a lower bound in reinforcement learning exists only very certain special cases like tabular MDPs.
Mm-hmm.
The linear MDPs model, that is a bit easier to analyze than the exponential family model, do not currently have the necessary lower bounds also. So it's a pretty much open area to see, because I showed some constants alpha and beta, which depends on the non-linearity of the problem.
Mm-hmm.
I will assume that a lower bound can characterize the exact scaling of this non-linearity. and the upper bound might be loose in terms of the scaling with the nonlinearity parameters, but the scaling with respect to t is quite is probably tight.
Thank you.
Maybe I can ask you one question, because you mentioned hyperparameter tuning as an application of the kernel Bandit, correct? So how would this work? You would sample and run the whole deep neural network, optimize it, and get the loss. And that's how you plan to operate this? And
so suppose,
have you done that?
No, I have not done that, but there is a lot of whole number of people, the practitioners, they are doing on that. In fact, there is a company called Sigopt who actually does this as part of their business. So they just tune the parameters. So you give your machine learning algorithm, they'll tune it for you.
So are you saying all these students who are sitting and turning knobs on deep neural networks are all wasting their time simply using?
Yeah, so there are a lot of papers you can from Google, I think, and from other groups also. You can get that they are tuning deep neural networks using this GP-UCB algorithm or any kind of GP models. They are just Bayesian model they're building, and they're just tuning this.
And it works, meaning
with
few tries. What is, like, supposing a typical training schedule for like an ImageNet or something takes, let's say, a day on a very deep neural network. How many? So you would not want to do this over 20 days. So what kind of time would it take to?
So magic? So it's like it will obviously depend on the data and also the size of the neural network. But it has been shown that in some papers I have seen that they are tuning it in 50 rounds. That means they are just running this Bayesian optimization GP-UCB algorithm for 50 rounds. So
but how many parameters are we talking about? Like how many hyperparameters are we talking about? Just the learning rate, or are there lots of hyperparameters?
There can be lots of, like, learning rate is the main, and basically learning rates, number of layers, and number of units. These three are top hyperparameters to tune. The others you can fix also. But these three they are doing and just running for 50 times. And they are showing that after 50 runs, that means 50 times you have to train your model on the ImageNet. Then you can converge on the best possible hyperparameter that will give you good test results. Okay, cool. Thank you. Any other questions? Otherwise, we'll thank the speaker for a fantastic talk. Thank you very much.